Hello my dear student, welcome back to the channel Life is Chemistry by Dinheki to visualize the chemistry. Today we will discuss another topics of organic chemistry, that is the preparation of ether. We can classify the ether into two categories, which is the symmetrical ether and unsymmetrical ether. Here the group which is attached to the oxygen is same. This is the symmetrical ether. But when the group which is attached to the oxygen atom is different, this is the unsymmetrical ether. Here R and R1 are not the same, so this is the unsymmetrical ether. We can prepare this symmetrical ether very easily from the alcohol. If we take same types of alcohol ROH and it will be dehydrated at 140 degree centigrade temperature, we can easily prepare the symmetrical ether. Now if we want to prepare the unsymmetrical ether in the same process, that is the dehydrating process, then we have to take ROH and another alcohol which is R1OH, and we have to dehydrate it in 140 degree centigrade temperature. When we dehydrated it, we face a problem. The problem is that our main product, that is unsymmetrical ether, is produced, as well as there will produce some symmetrical ether which is ROR and R1OR1. So unfortunately we get a mixed up product of ether, and this ether cannot be separated easily as they are the same types of compounds. So we are facing a problem to prepare or synthesis the unsymmetrical ether by dehydrating methods. Then what will be the solution? The solution is we can prepare the unsymmetrical ether easily by Williamson ether synthesis. Not only the unsymmetrical ether but also the symmetrical ether can be prepared by Williamson ether synthesis. So today we will discuss about the Williamson ether synthesis, its mechanism and its application. Now we want to prepare these types of unsymmetrical ether which is ROR1. To get the initial product or initial reagent, we want to cut at this point, and this cut is heterolysis cutting. After the heterolysis cutting, we get two components with different polarity, that is, one will be negatively charged, another will be positively charged. As we know that the oxygen is highly electronegative and it will want to acquire the negative charge, so basically RO component will possess the negative charge, and another component after cutting we will get R1, which will be the opposite to the first one, so it will be the positively charged. So R1 component will possess the positive charge. This is the precursor of the starting material to prepare the unsymmetrical ether. Now what will be the starting material? This starting material can be obtained from these two charged precursor, and this will be the alcohol ROH, which has the detachable proton or acidic proton from which we can easily get RO minus, and another one is the alkyl halide where the carbon has the polarity of positive charge. So by combining this alcohol and the alkyl halide in proper condition, we can obtain this unsymmetrical ether. First, the alcohol will be treated with NaH, sodium hydride, which is a base. This base will abstract the acidic proton from the alcohol to produce the alkoxide ion, which is RO minus, and this alkoxide ion are able to react with the alkyl halide where the carbon atom which is attached to the halogen has the polarity of positively charged, and it will produce the unsymmetrical ether which is ROR1. Here the R group, which is coming from the alcohol portion, may be alkyl or aryl group, and R1 group may be the unhindered alkyl, aryl or benzyl group. Here X is the maybe the iodide or tosyl group. And for this reaction, we have to use some solvent. The solvent is the benzene, toluene or dimethyl formamide. It will be the solvent. Now, do you recognize this reaction? If we closely look at the reaction, we can see that the alkoxide anion will react with the alkyl halide. Here, the alkoxide anion behave as a nucleophile, whereas the carbon attached with the halogen group in alkyl halide group, it will behave as electrophile. So basically the nucleophile react with the electrophile. So this is the basically a nucleophilic substitution reaction, and it is a SN2 reaction. For being a SN2 reaction, the R1 group, which is attached to the halogen or which is the part of the alkyl halide, should be the primary carbon, but there is no limitation or no condition for the R group, which is the part of the nucleophile. Now here is some example to prepare some symmetrical and unsymmetrical ether. First, we have take methanol, which will react with the sodium hydride to form methoxide anion. Then it will react with methyl bromide to form dimethyl ether, which is the symmetrical ether. And this symmetrical ether is produced by Williamson ether synthesis. Second one is, if we take ethanol and it will allow to react with sodium hydroxide, sodium hydride, it will produce ethoxide anion, and again it will react with the methyl bromide and it produce ethyl methyl ether, which is an unsymmetrical ether. So both the symmetrical and unsymmetrical ether can be prepared by the Williamson ether synthesis. Now we want to prepare this ether which contain a ethyl group and a tertiary group. Now this ether should have two types of starting material. One types of starting material contain the tertiary butoxide anion and ethyl iodide. Another type of starting material will contain the tertiary butyl iodide and ethoxide anion. Now question is that which pair or which pair of the starting material should able to prepare this ether. If we take the tertiary butyl iodide and ethoxide anion, there will be problem, because we know that the Williamson ether synthesis is basically a SN2 reaction. For SN2 reaction, the leaving group should be attached to the carbon which is the primary carbon, but for tertiary butyl iodide, the leaving group iodine or iodide will attached to the tertiary carbon. So it is the bad choice for the preparation of our targeted ether. If we start with tertiary butyl iodide and ethoxide anion, this ethoxide anion will behave as a base, and first of all iodide will leave from this alkyl halide and it will form a carbocation. After that, the ethoxide anion behaving as a base, it will abstract a proton to form the alkene. Basically this pathway will be undergo via E1 reaction. So from this the starting material we cannot get our desired ether, rather from this we get a alkene by E1 reaction. So another pair or another choice where tertiary butyl alkoxide is a nucleophile and ethyl iodide is an electrophile, which is the best choice for the preparation of the ether, and here SN2 reaction can be performed easily as the leaving group iodide is attached to the carbon, which is the basically primary carbon. So reaction with the tertiary alkoxide anion with the ethyl iodide, we can get our desired ether. If alcohol group and the leaving group are present in the same molecule, then Williamson ether synthesis produced via intramolecularly, and it will produce some cyclic ether. Here the OH group and the bromide group are in the same compound. When it will treated with the sodium hydride, it will form some anion, and this anion intramolecularly reacted to form a cyclic ether, which is nothing but tetrahydrofuran. Now we want to prepare this tertiary ether with the help of Williamson ether synthesis, or biphenyl ether with the help of Williamson ether synthesis, or we can synthesis of ether from the esters. After learning the concept of Williamson ether synthesis, can we perform the reaction for the preparation these types of ether with the help of Williamson ether synthesis, or it can be done by another way? This will be discussed in our later video.